So 14a, we just had F equals kx, so if I take this thing and I squish it over to there, then the k was 85 and the x was in meters, 0.473, right?
Yes.
So you just multiply those together and we got 40.2. So that was the maximum speed, or the maximum force that the spring would exert. Now, to find out how fast it's going, again, we said that we could do it two different ways. We could either do it from an energy point of view or a kinematics point of view. From an energy point of view, what we're saying is the potential energy in the spring turns into the kinetic energy of the block. So the potential energy of the spring was kx squared over 2, and the potential, or the kinetic energy equation, of course, is mv squared over 2. Now, since I end up with a 2 on both sides, mathematically, that becomes insignificant. So if I'm looking for how fast it's going, that would be the velocity. So m is going to come down to here. And then to get v by itself, I need to unsquare it. So we know our k was 85. And we know the x that we pushed in on it was, again, 0.473. But that gets squeezed. And we divide that by our which was 0.68. And we square root that whole puppy, and we get if you plug that in correctly, you should get 5.29 meters per second. That's the energy point of view. The kinematics point of view is pretty straightforward too. The kinematics point of view, we're going to basically use this to solve for VF, but the A comes from the idea that we have F equals MA. So A is going to be F over M, so I could replace this with that. Initially, when I squish this backwards, when I get it to x equals negative A, it's going to have an initial velocity of 0. So that part's going to go away. And so basically we get VF equals the square root of 2AD. But again, the A is really F over M. So we get 2F, I should put an A in, 2F over M. Everybody catch that algebra?
Yeah.
Okay, so we're just replacing this into there. So we end up with this, and so then you say to yourself, okay, no problem. I know 2, and I know my D was, again, 0.473. I change that to meters. I know the M is still 0.68. The only trick here is, what is my F? And everybody wants to jump over and say, oh, it was 40.2 newtons. We calculated that already. But this had 40.2 newtons when I'm here, but how much force did I have when I was at the equilibrium point? 0. So it didn't stay a constant 40 this whole time. It was 40, then it was 39, then it was 38, then it was 37, all the way down to, it got to 0. Now, again, if the spring works in such a way that the graph of the spring turns out to be some curve, then we would have to use calculus. But it doesn't work like that. A spring always makes a nice straight line. Since it's a nice straight line, the math is super easy. You just say, hey, if this is 0 and this is 40, then this is 1 and this is 39 and this is 2 and that's 38. The average ends up being, what was the average? What is the midpoint? So that's just going to be 40.2 divided by 2, or 20.1. Does that make sense? So if you stick in the 40.2, your answer is going to get too big, but if you stick in the midpoint, you plug this in and you say, hey, that comes out to be the exact same number, because it should work no matter which way we look at it. Does that make sense? Groovy. And again, in 14C, all we're doing is we're saying if I want half a cycle, if I start my half a cycle at the midpoint, then I'm going to go back and forth and end up in the same spot. So that would be minimum. But we want the maximum amount, so I have to start at one end and go to the other. A whole cycle would always come back to the starting point, but here, half a cycle would just go between negative A and A, so I'm basically just going to have the 0.473 times 2, because that takes me to the midpoint, and then same distance on the other side. So that part was super duper easy. 14D, we want to know how far is it going to go if, again, I shove it backwards, compress it nicely, but they're not really hooked together, they're just pushing on each other. So once it gets to the midpoint, then the spring at that point has already expanded as much as it wants to. The block just continues to move over. As the block continues to move over, how far is it going to slide? Well, we're going to use the same equation, but now we're going to solve it for D. So if we equation that for D, then we're going to get D equals BF squared minus BI squared over 2A. But again, the only thing slowing us down is friction, and when friction is the only thing slowing us down, then this is our A equation. So basically we can pull A out from here, and we can replace it with mu G. So we're going to slide until we stop, so my VF is going to be 0. My initial velocity, we just figured out 2 different ways, is 5.29 where. And then we divide that by 2, and we divide it by mu, and we divide it by G, and the mu was 0.2136? 2137. Yeah, I can't memorize it. So if you plug those in correctly and divide by, you get everybody's favorite number. 6.66 meters. Okay. Whatever. Some of you got 7, some of you got 5, some of you round too much, some of you don't round enough. It's okay. And our last part is if I take this now and hang it up or hang it vertically, so now the spring is this way, and I want to know how much does this string spread? Yeah, I can talk. So that's just going to look for how far did it move here. So the K needs to move here. And so the force, of course, is going to be what is actually doing the pulling is the weight of that thing. So the weight of that thing is 0.68 times 9.81. And the K we already said was 85. So that gives us 0.07848. 848. 848 meters, which is 7.8 centimeters. So that's a reasonable amount of stretch from hanging the weight. So that's it. Yay.
Let's go.